Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So, a few things to start us off today. So a couple of announcements, a bit of fun, and then we'll do some stuff. So first of all, just want to let you know that from Wednesday through Friday this week, I'll be away. I'll be in Perth. So we'll have our lecture on Wednesday, and then I've got to get on a plane and go to Perth, and I'll be back on the weekend. So if you email me between Wednesday afternoon and Friday, you might not get an answer quickly because I'm in meetings over at UWA. I'll try to answer things while I'm away because otherwise the pile gets bigger and bigger and so on. But and the other thing you have to factor in, of course, is that if you expect an answer at 4 a.m. 4 a.m. here is 2 a.m. in Perth, so that ain't happening, right? So yeah. So anyway, I'll be away in Perth from Wednesday afternoon till the weekend. So, yeah, prepare yourself for that. I'll try and answer emails, but it might be a bit more difficult. So that's thing one. Thing two, now I've put something up here on the Wattle page, which is new, which is the R quiz. So it's not accessible, so don't worry. It's not for your mark or anything. But we're now at the point where you're starting to think about the assignment. You've probably been spending some time learning R, so it's time to challenge yourself to see how you're going with R. So I've got an 11-question R quiz that I've now made live just now. So give it a go. It's multiple choice. You can either sit there and try it out without R in front of you, or you can sit there with R in front of you and see what happens. It's basically just meant to give you a little bit of feedback about how you're going learning R. It's pretty tricky, right? I thought of tricky things in R that you might not yet know how to do, but which will possibly be useful for you as you do the assignment and so on. So that's worth doing. Okay, there's no time limit, it's not for assessment, so there's no pressure involved, but I think it's just good for you guys to have a bit of a practice with R that is a bit more interesting and challenging than just thinking that you've got it all nailed. Okay, so that's thing number two. Thing number three is a bit of fun. This web page came up on Flowing Data the other day that Nathan put up a link to these guys from Data to Viz, which I thought was a really nice page and worth showing you. So it's a collection of Data Viz caveats. So I was talking about good and bad practice in graphics. I think this is a web page worth spending a little bit of time looking at. So I've linked to that on the interesting links page. And it's got a few things that we've talked about and we will talk about going forward. And they're all collected here in this sort of very interesting kind of display, right? So things like play with the histogram bin size, box plots. So we've talked about some of this stuff already. Some of it we will talk about. So I just thought this was kind of fun. And it's presented in a really interesting way. From Data to Viz, it's not clear to me actually whether these guys are statisticians or computer scientists or so-called data. There's this now group of people who call themselves data visualization experts and so on. We used to call that statistician, now it's got a different name. So these are worth having a look at. So, you can drill down here, so the spaghetti plot, right? So it shows you different types of plots here and how you can improve on them and so on. And this might come in useful, right? So worth having a look at. So that's my little bit of fun for the day, is this new link on the Interesting Links page. All right, more serious matters. So the assignment, you've now got all the stuff you need to do it based on the stuff we've covered in lectures. So people, are getting going on it. And this has meant a bit of a flurry of emails yesterday, which is cool. And so I've answered all those emails, but some of them raise questions that more of you might have. So rather than answering them one by one, I'll try and address it here. And I want to talk a little bit about what I expect for the assignment, because again, there's some questions around that. So let's try and cover that off. So the assignment's here, right? So you've all seen it. The instructions are much longer than the assignment itself. And the instructions cover pretty much what I expect you to do, but I'm going to talk more through that. But the assignment itself, it says the heights in inches of the singers of the New York Choral Society in 1979 are contained in a list called Singers. It's got components soprano.1, soprano.2, alto.1, alto.2, tenor.1, tenor.2, bass.1 and bass.2. 8 groups. It says these components are listed in order of decreasing pitch, by which I interpret that to mean the 8 groups are in decreasing pitch. Soprano 1 is the highest, soprano 2 is the next highest, all the way down to bass 2, which is the lowest pitch. Okay? The first 4 components are female voices, so 1, 2, 3, 4. The sopranos and the altos are all female. The tenors and the basses are all male. Okay? So both soprano groups are female, both alto groups are female, both tenor groups are male, both bass groups are male. That makes sense, right? Soprano, that's that high voice. Males generally in a choral society would not be singing soprano. There are boy sopranos, but they ain't in the New York Choral Society, so that's all good. Okay? Now the question says, describe and compare the height distribution with particular reference to what factors appear to be important in describing height. So we're looking at height distributions, distributions of heights. Well, we've got 2 factors, right? Gender, male, female, and pitch. And there are 4 pitch groups, of which are divided each into 2. Right? So gender and pitch are the factors. So the question really is, you've got to explore how do gender and pitch affect height. Okay? Now, let's be clear, we don't think that these are causal relationships per se, right? But we do, I mean, the data's got things in it that are not going to surprise you at all. You're going to learn that, gee, males are taller than females on average. Right? Not every male is taller than every female, we know that, but on average, males are taller than females. When the data reveals that, none of you will be surprised, okay? But this data has deeper secrets, and the goal, I guess, is to try and find out what those deeper secrets are, okay? Now, you're going to need to look at the data. So a few people have said to me, I can't find the data. Okay, here's how you find the data. It's in the class data, okay? It's in the class data. So I'm just going to go through this again so you can see. So you go onto Wattle, go to the software section, click on class data, it'll download it. So we're going to download that to the desktop just for fun. Okay, save. Okay, class data is now saved. Go into RStudio, come over here, go to the little open icon, click on that. Find the document you just saved, it's on the desktop, boom. Well, before I do that, let me just show you, before I load it, no singers, right? Object singers not found, so it's not there yet. Open the class data, where was it? Desktop, class data, okay. Now if I type singers, voila, there they are. Okay, there they are. Now, singers is a single object, so I'm just going to get you started here. Singers is a single object, it's a list. Okay, so maybe the first thing you're going to want to do is separate out the different components of the list. Okay, there's a couple of ways to do that, but I'm going to just say SOP1 is equal to singers dollars soprano dot 1. Okay, now if I type SOP1, I get all the soprano 1 group. Okay, so I can do this for all 8 groups, right? So SOP2, you don't have to use the same silly name I'm using, I just don't want to type a lot. Singers dollars soprano dot 2. Okay, and then SOP2 has something in it. I can do this for all of the 8 groups. So the first thing you're going to want to do is probably separate out the groups so you can deal with them one by one. If you don't want to type all that, that's cool. If you type singers and you'd use double square brackets 1, that'll give you the first group in a list. So in a list, there are 2 ways you can access elements. you can either use the name, so singers dollars, and then the name, soprano.1, that works. The other way, if you don't know the names, or if you don't want to type all those names out, you can just use that double square brackets, and that'll just give them to you in order. Double square brackets 1 will give you the first, double square brackets 5 will give you the fifth, and so on. Okay?
Can you attach it as well?
Nope.
Sorry.
Nope. So that's not a data frame. So data frames you can attach, lists you can't.
I attached it and it worked.
Well, you're lucky. Maybe R has matured since I last tried that. You never know, they keep changing R, right? Every couple of months they bring out a new version, and then a few things I say get easier or harder. So, yeah, cool. Okay, so I'm told you can attach it. You can try that if you want. That's cool. Okay, so that's how you get a hold of the data. Now, what you do with that, totally up to you. So I'm getting emails that are asking me, can I use t-test? Sure, do what you want. Can I use ANOVAs? Sure, do what you want. Right? Can I use a hammer? Sure. Whatever you want to use. You do whatever you want. Okay? Whatever you want. Now, as you're doing whatever you want, remember the name of this course, Graphical Data Analysis. Right? Graphical Data Analysis. Graphical. So if you do stuff and you just hand in 4 pages full of numerical analyses, you're going to be very sad at the end. Right? Because there ain't nothing graphical about that. Okay? So, you know, I mean, I sort of expect you're going to analyse it graphically. That doesn't mean you can't use other tools. You want to calculate means and standard deviations? Sure, go for it. Right? Now, whatever you do, you've got to find meaning in that. So, I mean, you can calculate the mean of all of the groups and you can report that, but unless you've got something sensible to say about it, probably best to stay silent, right? So, and you might be able to do that in a picture better, okay? So you're able to use whatever you want. I don't care. It doesn't have to be a method I've covered. Whatever you want, okay? But just remember, graphical is where we're headed with this course. And you can come up with some very graphical explanations for this data, okay? So go for it. All right. The other thing I'll say about it is the data sets are relatively small. So when you're constructing your densities and your histograms and all those kinds of things, you don't expect things to look beautifully normal. Like when we create 1,000 data points from a normal distribution and that thing looks like a dead bell, that's cool, but that ain't going to happen here because real data, small data, there's going to be bumps. And you're going to work out what window width will give you the level of bumpiness you're comfortable with, okay, in order to display the data and stuff like that. So these are choices I want you to make. You've got to make choices around things like layout. You've got to make choices around things like what graphs to choose. So a lot of people will ask me, what graphs do I choose? And my answer to that is always going to be, not my choice, your choice. Okay? If I choose it, I'm doing the assignment. I'm going to get 100%. Right? But that ain't the way it's meant to work. Okay? So, yeah, your choices. Your choices. All right, now, what do I expect in terms of a report? You've got 4 pages. That includes everything you're going to hand in. 4 pages. So that includes all the graphs and all the text. Okay? You do not have to give me your R commands. Okay? The reason I don't want your R commands is if your graphs look good, then you've done them right in R. If your graphs look wrong, your R's wrong, and I don't need to know how, I just need to know it's wrong. Okay? So, I don't need to see the R commands. You just need the 4-page report. It should be in the form of a report. So I want to see an introduction, I want to see a conclusion, I want to see a middle. Right? Write it like you're writing a report to your boss next year. Okay? So introduction, middle, conclusion. Set it out like a report. Now, I'm not going to be a grammar Nazi. I know that's a dreadful term, grammar Nazi. Right? So it doesn't have to be in perfect grammar, but it does have to be readable. And I get that, people's English varies. Some people speak, the Queen's English, and some people wouldn't even know who the Queen is, and that's fine. But it has to be readable. It has to be, you have to explain yourself well enough, okay? But, if you don't put a full stop in the right spot, you're not going to get penalised for stuff like that. So, the grammar has to be okay, but that's not what I care about, okay? Now, you know, in terms of how many graphics can you fit in, well, you've got 4 pages, right? And don't make stuff microscopic, because I'm over 50, right? And as soon as I don't even know you're here now, right? So, you know, if you hand it in and it's in 8-point type, I can't read it. When I can't read it, I won't read it. It's just like that, right? Because it just reminds me how old I am. It makes me sad, all that stuff. So I'm suggesting, you know, 11-point type's kind of the smallest I can reasonably read. Font is up to you, but, you know, use the default, right? Word chooses Calibri or Times, depending on what computer you're on. Those are fine, you know. Don't choose some weird-ass font. You know, don't produce your assignment in Ransom Note. That's so 1980s, whatever. Okay, so don't do that. So just sensible is what I'm wanting. Now, you know, people say, what about margins? Okay, remember what the goal is here. The goal is to describe this data for me. It is not to squeeze as much ink onto that piece of paper as you can possibly do, right? So on this side of the goal, the 4 pages isn't meant to drive perverse behaviour, okay? You know, yes, you could fill 4 pages using 2mm margins and 2-point type, and yeah, you get a hell of a lot more text in. But guess what? It's terrible, unreadable, etc. So just be sensible, okay? Just be sensible. So I'm not going to sit there and go, oh, that's 10.5-point type, and I asked for 11. Of course I'm not going to measure it, but just be sensible, right? Just be sensible. I'm going to police the 4-page rule. So 4 pages is 4 sides of a page, okay? 4 pages, 4 sides. So you can do it on 2 pieces of paper, front and back if you want, or you can use one side, I don't mind. But if you go over, basically the reading stops at the end of 4 pages. So why am I doing that? Well, that's so the rule's the same for everybody, right? That's it. That's the only reason. Because, you know, if I allow someone to use 5 pages, they sneak an extra graph in. That's not fair, is it, right? So we'll stick to the 4.
What's the minimum?
Oh, 0. You can hand in 0 pages, that's the minimum. You won't do very well, but yeah. No, there's no minimum. If you could explain this data in half a page, go for it, okay? I mean, I don't think that's going to work out, but, you know. I have seen a good solution to this in a couple of pages. Yeah. But, I mean, not a brilliant solution, but a good solution, so it's cool. Everyone's solution should be different, by the way, right? You're going to see different things. Your main conclusions are probably going to be the same, but you should write it differently, and you might choose different graphs, and that's cool as well, right? So, you know, don't ask me, should I choose histograms or densities, because my answer is going to be up to you. Very simple, okay? So, you know, in things where you have choices, I want you to exercise those choices. But I don't want you to be timid about it. Okay, just be brave. You'll discover in life that being brave takes you a lot further than not. And, you know, this is not crazy brave, right? This isn't, you know, tackling the hijacker on a plane or anything like this. This is just making a graphical choice. So, you know, stay calm about it, you'll be fine. You'll be okay. Now, what can you... So that's what I expect to see. Now, what can you expect in terms of how the marks will look? Okay, let's be clear. This course doesn't have exams, right? So I can't, you know, give you, you know, high marks all through the semester and then assassinate you on a tough exam, like you know happens, okay? So I've kind of got to be as tough all the way through as is reasonable. So, you know, when you get the assignments back, don't expect 10 out of 10 or whatever it is. I mean, 10 out of 10 means you nailed it perfect, and that's just not going to happen for everybody, okay? Marks will be anything from, you know, 9 point something down through, I don't know, 2 point something, whatever. That's fine. I mean, if you're on the 2, you're probably not a happy person. I get that. Now, having said that, the history in this subject is pretty clear. People don't fail at GDR. I mean, it's hard to fail courses when you only have assignments, right? You've basically got to just turn up, do something reasonable, and you'll pass. Now, I get that people don't want to come to this class and get 50p. I get that. So you want to do better than pass, obviously. But nobody should be sitting in their seats quivering because you might fail, right? Failure requires significant effort. in this class, let me tell you. And you have to, and you could do it, right? You could produce graphs that just piss me off, you know, and that one year someone did, and that's cool. They didn't do so well, you know, because we have all these rules for graphics, right? We've talked about them. You know, line things up and put titles on everything. One year someone handed in, everything was higgledy-piggledy, nothing had a title. Of course they did badly, okay? Anyway, that's life. But, you know, you're not going to fail if you hand in something half sensible. And, you know, you're all sitting here today, right? You're coming to class, so you're probably going to hand in something half sensible. So my best advice is don't fret about this course, you know. And when you get the marks back, here's the phrase I don't want anyone to say to me. I've failed. No, you haven't. Even if your mark is 2, you're probably going to pass because things get scaled into you. Okay, so everyone should just take a chill pill. Actually, don't take any pills, pills aren't good for you. Chill, just chill, and we'll all get through it. Okay? So, that's what I want to say, yes sir.
I agree that provide the data field like this, or add some data, provide the data set decreasing and add some records as well.
Yeah, good question. So in the instructions it says you can only use stuff what I tell you. I'm happy for you to do research on singers and vocal cords. Like I said last week, I just don't want you looking up this data set and a canned analysis of this data set. Because, you know, the internet, if you want to find anything on the internet, Google will find it for you, right? I mean, just this morning, I looked up, where do I run in Perth, right? Because I've got to go running when I'm in Perth. And I now know all the places I can run in Perth, so it only took me 10 minutes. So, you know, if you look up analysis of New York Choral Society singers data, guess what? You will probably find a solution to this assignment. They might not do very well, by the way. I know where they are, I've seen them, I wouldn't give them high marks, got to be honest. But, having said that, so just don't do that. You want to look up things about singers and how, you know, vocal cords affect pitch and all that, go for it, that's cool. So if you do that, just reference the URL. I'm not one of these people who says you can't use Wikipedia. Why not? It's on the internet, it's mostly right. That's all cool. So is that fair enough? Yep. Any other questions? All right. So we all roughly know what to expect. Yeah? Okay. So look, if you have any other questions, feel free to email me. But I just wanted to put it all down on the table today so that we're all on the same page. And again, the main thing is just try and do something. Yeah, what you should do with these things, and I know it's almost impossible, right? Because when you've got an assignment, you see it through the prism of what grade am I going to get, and that's a terrible way to live your life, to be honest. Because at the end of the day, I did university over 30 years ago, and I honestly just can't remember what my grades are, and it didn't matter, right? Because I'm standing here in front of you and they're paying me the small dollars and all that. But I stand here by choice, right? I'm doing the job I love to do, so it didn't matter, right? So you should take that, I mean, you can't take that attitude entirely, but don't think about it as I'm going to get a good grade by writing the best assignment. Think about it as, I'm going to learn something about this data set, I'm going to display it in a way that, you know, has the person reading it thinking, you know what, I know more about what's going on here. Attack it like that, and that's your best bet. Okay, any other questions? No, okay. So what we're going to do is, before each of the assignments and for the project, I'm going to have this chat through. So there's 2 assignments and a project, so this is the chat for the first one. We'll have a chat about the second one, we'll have a chat about the project as well. When we have the chat, that's generally a sign, time to get started on it, okay? Today's the 13th of August, I think it's due on the 22nd, yeah? Something like that. That's heaps of time. 4 pages, right? You could write that in about half hour. Okay, an hour. 2 hours if you think. You know, you've got days now. So, and I know, look, by the way, please no one complain that I've got other things to do, I've got all these other, I know. And the workload in this course is not dramatic. So, all good. One last thing, look, if something bad happens to you and it means the 22nd you can't get in, you just come and talk to me, all right? There's reasonableness in behind this veneer of whatever I've got. Okay, let's move on. Now, we're going to talk about, so we're moving on to the next chapter now. And like for every chapter, there's a story, and this is a story about rats. Okay, so and it's partly interesting and partly sad because the rats don't make it, which is pretty much what happens to rats when they're in. Well, if they live in any kind of medical facility, they tend not to come out, which is pretty sad. Basically, the reason most modern medicine works is essentially because of animal models, right? It's unethical to find out about how humans work by just cutting them open and seeing them, or by bleeding them or whatever, right? So we don't do that. We have much less of a problem doing this with animals, which is sad because, well, who has a dog? Who likes dogs? Yeah, see, and you wouldn't, so we can be sad for the rats. So, but there's a serious side to it as well, right? Because in human pregnancies, blood loss can cause loss of fetus, and that's tragic for the mum, tragic for the family, and of course it can cause other medical complications. So, medical researchers are really interested in knowing, what sort of problems can cause miscarriages and that kind of stuff. And one of the lines they've walked down is that they've got this idea that if there's a certain amount of blood loss, right, and so if bleeding in pregnancy is generally something you've got to go straight to the doctor and report. If there's a certain amount of blood loss, then it threatens the viability of the pregnancy, and that's very serious, okay? So, but they want to know if there's a way they can sort of work out when complications might arise. And so they've got this sort of tentative link between the amount of a particular hormone called AVP, arginine-vasopressin, I think it is, and blood loss. Okay, so and measuring the hormone levels relatively straightforward. Measuring blood loss, perhaps less so, right? So they want to see if there's a relationship between these two variables. Okay, can't do it in humans, so they get rats and they experiment on the rats. So we've got 92 rats. And they wanted to determine the effect of blood loss on secretion of the hormone AVP. So AVP is an important hormone for sustaining a pregnancy. Okay? So what they did was they induced blood loss to the rat by chemical injection. Then they measured the volume of blood lost and the level of the hormone. And they want to relate the two variables. Okay? So pretty sad. The rat obviously is not going to make it, but we have now X and we have Y. Okay? The goal is to try and understand the relationship between X and Y. And if we can understand that relationship, then that can help us understand the progression of a human pregnancy. Okay, so real data, real story, and obviously something that's pretty important. Okay, so let's think about this. So here's the data. So it's this is from the class computing notes. So the first thing to do is to read in the data. We've got some X's and we've got some Y's. So let me just read that in. There they are. You'll see X and Y have now appeared down here in my list of objects. They're 92 long, so there are 92 rats in the study. And we've got to relate these two variables. Now, most of you would already know that the simplest way to look at a relationship between two variables is simply to produce a scatter plot. And the command in R for a scatter plot is pretty simple. It's just plot x, y, and then, of course, we normally label everything up because we love to be neat. Okay? So here's the basic plot. And I'm just going to make it relatively large so you can see it, and then we're going to talk about it. So there's the basic plot. Okay. So that plot describes the relationship between blood loss and AVP. Now we've chosen blood loss as X, so that's my explanatory variable, and we are trying to see how that affects the hormone level. That's Y. Now, one good question that you should always ask when you're thinking about data sets that have an X and a Y is which one should be X and which one should be Y. And you know what? It's not always clear, right? There is no natural X or natural Y, okay? There used to be, back in the day when Sir Ronald Fisher, who one of the most famous statisticians ever, was around, he did a lot of what we call field experiments at Rothamsted Field Station in the UK. Now they have to do things like that in the UK because the climate there is bad, right? You can't grow a lot of food, but you have to feed a lot of people, right? So they did a lot of crop experiments at this place called Rothamsted. And so what he wanted to see, what Fisher often wanted to see is how the yield, which was Y, changed when they changed conditions for crops, you know, with things like fertiliser, water and all that kind of stuff. And those are what we'll call controlled experiments, okay? And in controlled experiments, the X's, the fertiliser, the water and all that sort of thing, were fixed. You could change them. The experimenter had control over those. So they meddled around with the X's deliberately, and then they saw how Y changed. So in that experiment, or that kind of experiment, there's an asymmetry. You control X and you measure Y, and you want to see how Y changes when you change X. So it's very deliberative. And you think about that in terms of changes in X, maybe not causing but being related to changes in Y, but you care about the changes in Y. And you don't so much care about the changes in X because you did those changes yourself, right? So that's a designed experiment or a controlled experiment. Most data these days is not of this type. Most data these days is what's called an observational study. In other words, you observe, you measure both X and Y, right? You don't control X in any meaningful way, you just measure it, okay? So for these rats here, they put a chemical in them and it induced blood loss, and then they measured the blood loss. They didn't deliberately, well, they deliberately did something. They deliberately did not induce blood loss in a bunch of rats, so there's 0 here. A bunch of rats did not get any blood loss, so they're sort of like a control group. And then, but every other rat beyond that had an amount of blood loss induced, and it was then measured. So this is an example of what's called an observational study. In observational studies, you don't control X in any meaningful way, so you don't know which is X and which is Y. The context of the problem tells you which is X and which is Y. So what is it you're interested in being able to predict? In this case, the doctors wanted to predict hormone level. So that becomes Y, okay? And so X is the variable they don't care so much about, blood loss, okay? It's measured, but they're not trying to predict that. They're trying to predict hormone level. So there's this asymmetry that's induced by the problem description, okay? Now, the other thing that you have to say, and you have to say this in almost every statistics course, because God forbid you should leave university and not hear the phrase, and you will have heard it before, correlation is not causation, okay? Correlation is not causation. Why do we keep having to repeat it? Well, we keep having to repeat it because humans have a defect. Humans have a defect. It partly helps us and partly doesn't. Humans have this intense desire to know why things happen, right? It makes us very curious animals, okay? So, you know, if you're a dog, dinner just turns up and you're owned by a nice human, dinner turns up every night. And you don't think, why? You just eat the food, right? And it shows up every night, okay? And you know dogs aren't looking for reasons why, because, you know, if an owner and a dog are out hiking and the owner dies, the dog just sits there, right? He doesn't ask, why is my human lying there not breathing? He just sits there, I'm with my master, right? And so, whereas humans would do something else. We need to know why. This is terrific, but it causes us to mistake very often correlation and causation, because what we do is we go, this changed and then this changed. Why? Why is that? And then, you've heard about conspiracy theorists, the people who wear the tinfoil hats, then you just make shit up, right? You go, oh, yeah, this changed, so it must have happened because, and then you've got some reason why that happened. So, you know, and there are lots of examples around of this, right? So, for example, do you know that in Florida, the land is sinking? The land is sinking into the water. So the coastline's rising in Florida. It's got absolutely nothing to do with the population of Florida, but it's also true that the population of Florida is rising, right? So if you look at X as population of Florida and you look at Y, which is basically rising sea level, okay, you will see that rising population is related to rising sea level. And you know, if you watch I don't know, Fox News, you might get the view that all those people heading to Florida is really weighing that down and it's sinking into the ocean as a result of that, right? Because God knows this variable's changing and this variable's changing at the same time. Why is that? Americans are heavy, we're all moving to Florida. Okay, that's it. That's what's going on. Okay? And you might think, well, that's just stupid. But this is the sort of thing people make up, right? And then once it's out there, people buy into it. And look, you might say to yourself, no, I wouldn't be smart enough, or stupid enough rather, to buy into that. But history is literally littered with what are called spurious correlations. In fact, so much so there's this awesome website that I'll show you. Let's go to an awesome website. A guy named Tyler Vigen. And it's called Spurious Correlations, and now he's got a book out. It's called Now a Ridiculous Book, right? And what he's done is he's taken all these different variables and he's shown how linked they are, and you try to think of what's the relationship. So, for example, US spending on science, space and technology is correlated, 0.9979 is the correlation between US spending on science and suicides by hanging. So science causes suicides, right? Yeah, well, they're correlated, but there's no causal link. This is a fun website, by the way. A bit hard to remember, but he's one of these, there are two types of people in the world, people who name websites after themselves and people who don't. So you've got edwardtufty.com, tylervigen.com, so that's his website. Okay. You won't find michaelmartin.com. Who needs it, right? So that's how you remember it. Anyway, that's pretty cool. And you can see all the weird things that are related, right? The per capita cheese consumption versus the number of people who died by becoming tangled in their bed sheets. And it's a problem, folks. It's a problem, right? Believe it or not. And you can come up with all sorts of weird explanations as to why this is true. Divorce rate in Maine versus the per capita consumption of margarine. You just slipped right off your spouse. That's it. Gone. All that. Yeah, and so on. Age of Miss America and murders by steam, hot vapours and hot objects. Whatever. Right? Anyway, fun site. So, correlation versus causation. I'll put up some links in the interesting links, which is just for fun to read a little bit later, which actually illustrate two big examples in science where correlation and causation was got wrong in both directions. In the 1950s, it was thought that polio was caused by sugar. Okay, so consumption of sugar could cause polio. It's known now not to be true, right? But I'll post the paper where you can read all about it. In 1951, the state of North Carolina in the US almost banned soft drinks because of this putative link between polio and sugar consumption. Okay, so imagine a world without Coca-Cola. Be good, wouldn't it? A Pepsi fan. So yeah, so that's one where they got it wrong, right? They said that was causally linked, and it clearly wasn't. But it wasn't so many years ago. So who here thinks that smoking cigarettes causes lung cancer? Who here thinks that? Is anyone here who doesn't think that's true? Smoke? Do you smoke? Used to. Why'd you give up? You'll be right. You don't think smoking causes lung cancer? You don't know. Okay. There's papers out there that kind of show it does, but we can read them. That's cool. By the way, you're in good company. About a long time ago, 50 years ago probably. So Ronald Fisher, probably the greatest statistician of all time, wrote a number of articles arguing that cigarette smoking does not cause lung cancer. Okay, and he tried to back it up with data, and he made up a whole bunch of nonsense and got it published. Right. So, and I'll post a paper here about that. And he was a smoker. He didn't die of lung cancer. He died of another kind of cancer. Buried in Adelaide, by the way. So, if you're a statistician, You ever go to Adelaide? That's the reason to visit, right? You might think it's a lovely place. No, Fisher died there. So there you go. So there's all these things, and these days we kind of know that cigarette smoking causes lung cancer. It's on the packet, for goodness sake, right? It's on the packet. Well, I had a friend who smoked, and she only ever bought the packets that said smoking harms your fetus. She wouldn't get the ones that said smoking caused lung cancer or the ones with the pictures of the teeth and stuff. And I said, why do you do that? And she said, because I'm never going to get pregnant. It's all good. Yeah, I know, weird, eh? Anyway, by the way, the tobacco companies would have liked people very much to believe that smoking didn't cause lung cancer. And they came up with a theory around why it didn't. They said, look, yeah, we understand there's correlation between smoking rates and lung cancer rates, lung cancer incidence. We know that. The data says that. Then they said, but correlation is not causation. The same thing we're saying here. And people went, well, hang on, what's going on then? And they said, oh, it's easy. People who smoke tend to engage in other risky behaviours, right? They hang out in bars, they do other things that are risky. And it's not the smoking that's causing them the problem at all. It's their lifestyle, their general lifestyle, their risky lifestyle, right? So it's not the smoking. They can smoke all they want. It doesn't matter. It's the other behaviours that are bringing them to lung cancer. They made that argument very seriously, okay? And they also paid a lot of money to congressmen and senators in the US, and for a very long time they made a lot of money until it became more obvious that, they're wrong. So, it's a really complicated question, correlation and causation. Statisticians, by the way, very rarely have the opportunity to actually say what's going on, because establishing causation is actually really hard, right? Really hard. You don't establish it by saying, I notice these two variables move together. That leads you to the fatal error that correlation and causation are the same, and they're not. Establishing causation generally requires help from outside statistics, other science, right? And so the question around lung cancer and smoking is about medicine, not about statistics. Right? It's about establishing the amount of cell damage that is done by exposure to chemicals that are in cigarettes. And they can do laboratory studies that don't involve people until they can show cellular damage that's consistent with cancer generation. And that's how they know. It's not really much to do with looking at observational data about one variable going up and the other variable following it. It's just not. So, anyway, it's a talk we always have to have in statistics classes, and it'd be wrong not to have it. But I didn't mean to interrupt the rats, so let's get back to the rats. Okay, so this is the relationship between blood loss and hormone level. Okay, I'm going to ask you some questions now. Tell me about this relationship.
It's not linear.
It's not linear. Okay, what is it? Okay.
It could be linear after a threshold.
It could be, okay, so we've got a couple of answers. So not linear and drew a curve in the air, cool. You reckon it might be linear here and then linear there. So piecewise linear, okay, but it changes. Yeah, fair enough. Okay, cool. Anyone want to use a quadratic? So we got the word quadratic. Quadratic? Any updates on quadratic? Any other words you want to give me? Don't understand the word.
Oh, you said parabolic.
Parabolic. Parabolic. Yeah, well, yeah, that's cool. Any other words? Exponential. Yeah. Exponential means, shallow and then rises more steeply. These are all good words. We're here in a third year stats class, so you guys have done enough statistics to know the big words, right? So linear, quadratic, parabolic, exponential, all these good words. Piecewise linear, these are complex words. Now, here's an encouragement for you. When you look at data, first thing you should do is pretend you're not over 20 years of age and try to think of it like a kid, like a small child, hopefully. So the first thing I would say about this data is it goes up, right? It goes up. It starts low and it goes up. As one variable goes up, the other variable goes up. So that's the first thing I'd say about it. The other thing I'd notice is that we all when we talked about it, we all only talked about what I would call location. That is where the curve goes. So all of you have imagined a curve. I'm guessing that for most of you the curve ran roughly through the middle of the data as you moved, and you ran all the way along. And so we only talked about location, but you know, you've done more than 1 year of statistics, right? So you know there's more to life than location. There's also spread, right? So tell me about the spread of this data. What happens to the spread of this data? Okay, beautiful. He said heteroscedastic. You've all heard that word before? Hetero, different. Scedastic comes from the Greek word for scale. So different scale. In other words, it starts off small scale, gets big scale. So the scale changes. So heteroscedastic is the technical word. Okay? Again, I want to encourage you to think like a child, because there's no child I know, not even my child, who's not a child anymore, who knows the word heteroscedastic. Right? Because I don't use it at home. I don't like to swear at home. Right? And so here's my encouragement. So we did something really good before. When I said, what's the shape of the data? Some people use their fingers. That's cool, because the finger doesn't tie you into quadratic or exponential or any function. It just follows the data. So I like that. That's really cool. Now I want you to use 2 fingers or a finger and a thumb, right? And start down the left-hand end, and it's sort of narrow. And then as you move across, it gets wider. And that's, the technical term is heteroscedasticity. But another simple way of thinking about that is the spread's not the same. As I move from left to right, it gets bigger. Okay? Now, the one thing we do know for absolute sure is that this is a complex relationship, not a simple relationship. Okay? It curves. We don't really know what the curve is, but not only does it curve, it gets spread out. Right? And a lot of people, so you guys have done statistics for long enough to know what heteroscedasticity is, right? You know that it means the variance changes. That's cool. But do you know why that matters? Why does it matter if things are heteroscedastic? If you know where the location is, why do you care if it gets more spread out?
The assumptions of non-replication.
Okay, but assumptions. Why do we care about assumptions?
If you are treating relationship between the two,
So you make assumptions.
Yeah.
Well, why do we care? It doesn't. Well, we don't know. The distribution could still be normal. It's just that its variance might change. So that's standard deviation changes, and the model has it as a fixed number. So we have to accommodate that in our model. We could do that though, right? So what's the underlying reason we care that things are heteroscedastic? Because we could build heteroscedasticity into our model. All we do then is we just say, well, sigma squared is not constant, it's related to x. We could do that. And we could fit a different model. That's all cool. But we actually do care about it, and we care about it for a non-technical reason. So I'm going to lead you there. Okay, if I'm down here and I say x is here, what's y? Where do you put y? There, right? And you're pretty sure, right? Because, you know, how far can it move? Right? It's going to be there. Now, if I'm up here and I say x is 22, what's y? Where are you going to put it? You're going to put it in the middle, right? So it's going to be up there somewhere. But how certain are you of that? You're not really, right? Because it could be in the middle, but it could be as low as here, and it could be as high as the top of the screen. And there's a massive difference there, right? So what heteroscedasticity does is it corrodes your ability to predict. Which brings me to human failing number 2, right? So we've had human failing number 1. We've got to have an explanation for everything. Human failing number 2, we like predicting, right? We love predicting. You know that's true. You know what the most popular website in Australia is? Who knows? Who knows what the most popular website in Australia is? The Bureau of Meteorology, right? Why is that the most popular website? Because you want to know, is it going to rain today? Or you want to know, when I get up tomorrow, is it going to be minus 10? Right?
it's true. It's quite true.
So, yeah, they're pretty good. They're pretty good. I sometimes go on AccuWeather and have a laugh, because it ain't. Yeah. So we love predicting things, right? Now, if we love predicting things, we probably love predicting them well, right? No one wants to predict something and have it just be hellishly wrong. Right, so if I tell you blood loss was 22, and I say, what's the prediction? You say, oh, it's 35 is my prediction, but it could be as low as 20 and it could be as high as 50. I'll think less of you because that's an enormously